Welcome back to another explainer. Today we're going on a bit of a mission. We are popping the hood on a true giant in the semiconductor industry. We're talking about the undisputed gold standard for circuit simulation, Hspice. If you've ever found yourself wondering exactly how modern microchips, the literal brains inside all of our tech, are designed without just catastrophically failing the second you turn them on, well, you are absolutely in the right place. Here's our high-stakes survival guide for the day. We'll kick things off with the silicon stakes, dive deep inside the Hspice netlist, unpack the big three analyses, face the terrifying convergence nightmare, and finally, look at how all of this powers our digital world. All right, Section 1. The silicon stakes. Building without blueprints. Now imagine trying to build a multi-billion-dollar skyscraper completely blind. No blueprints, zero structural simulators. Sounds crazy, right? Well, in the silicon world, the stakes are actually even higher than that. Just consider the sheer terrifying scale of modern hardware for a second. Today's advanced system on chip packs over 50 billion transistors. That is 50 billion with a B. When you're dealing with that kind of mind-boggling microscopic complexity, you literally cannot just cobble together a prototype on a breadboard on your desk to see if it works. Physical trial and error, yeah, that's completely impossible here. So hardware engineering gives you exactly one shot. The industry calls this tape out. It's that final, nail-biting moment a design gets sent off to the manufacturer. And if there's a bug, even a tiny microscopic one, you can't just push a quick software update over Wi-Fi. No way. A failed tape out means manufacturing a brand new physical mask, costing millions of dollars and delaying your product by months. It's an absolute nightmare for any engineering team. So having precise simulation isn't just a nice to have. It is literally a multi-million-dollar insurance policy. And this whole ecosystem actually traces its roots all the way back to the 1970s at UC Berkeley, which is where the original SPICE framework was born. Over the decades, out of dozens of variants, Synopsys Hspice rose up and established itself as the absolute commercial gold standard. Why? Simply put, unmatched numerical accuracy, incredibly robust algorithms, and foundational trust with silicon foundries. Basically, when Hspice tells you a circuit's going to work, silicon engineers implicitly trust that data. Moving right along to Section 2, inside the Hspice netlist, the language of circuits. Let's step from the high-stakes theory down into the actual microscopic code that runs this engine. Now, if you're used to modern software, you're probably expecting some flashy drag-and-drop graphical interface, right? Well, Hspice doesn't care about looking pretty. The raw engine executes its wildly complex math entirely through plain text files, usually formatted as .sp files. It's a strictly code-driven way to represent physical hardware. So every single netlist is built using these strict anatomical blocks. First up, you have your title line, simple enough. Then come the element cards, which actually declare your hardware, like telling the system exactly where a 50-ohm resistor sits. Next are the models and libraries. This part is absolutely crucial because it's where physical reality meets the software. It uses proprietary equations from foundries to describe exact transistor behaviors down at, say, 5 nanometers. After that, you've got control cards to tell the engine exactly what calculations to run. And finally, you wrap it all up with a mandatory .end statement to tell the simulator to stop. Okay, quick story time. Here's a classic industry beginner trap. Why do the brand new junior engineers simulation completely fail on day one? Well, it's because of a hard-coded rule in Hspice. The very first line of a netlist is always treated as a comment and completely ignored. If you accidentally type your actual circuit declaration on line 1, the simulator just drops it and everything fails or goes completely crazy. It is totally a rite of passage for every silicon engineer to make this mistake exactly once. Which brings us to Section 3, the big three analyses. The diagnostic toolkit. Think of these fundamental simulations as a highly specialized medical toolkit for evaluating a circuit's structural integrity. First in the kit, we have the DC operating point, or .DC. This calculates static voltages and steady-state nodes when the circuit is just resting. It's literally like checking a patient's resting heart rate before making them run on a treadmill. Then we have transient analysis, .tran. This tracks dynamic behavior across time as signals flip between binary 0 and 1 over fractions of a picosecond. It's very much like recording ultra-high-speed video to catch those tiny, rapid, microscopic interactions. And finally, AC small signal, or .AC. The absolute best analogy for AC analysis is acoustically testing a high-end speaker. You want to know exactly how cleanly that speaker hits the deep bass versus the high treble, right?
Well, AC analysis sweeps independent input signals across massive frequency ranges to test electrical bandwidth and gain. It ensures your circuit can actually handle the specific signal frequencies it'll face out in the real world.
On to Section 4, the convergence nightmare, when math crashes. See, occasionally, if a circuit transitions just a little too rapidly, the numerical methods crash, and the simulator gets caught in an infinite mathematical loop.
When that happens, the engine tries to slice time smaller and smaller and smaller until it just violently gives up, and it throws this infamous, dreaded error, time step too small in transient analysis. Let me tell you, seeing that text pop up on your screen is enough to send a shiver down any veteran designer's spine. It basically means your simulation just hit a brick wall. Overcoming this specific convergence failure, that is the ultimate test. It's honestly what separates the elite master designers from the novices. The masters know exactly how to mitigate these disasters by diving deep under the hood. They tweak specific engine parameters, like adjusting the dot options con step, or carefully modifying relative tolerances. They gently guide that mathematical engine right past the bump without sacrificing the integrity of the data.
And they have to do all this while accounting for process variations. Because silicon chips have to work flawlessly in some incredibly unforgiving environments. We're talking inside the blistering hot core of an AI data center, or out in the absolute freezing vacuum of deep space. Plus, you have to factor in physical manufacturing tolerances, because no two transistors are ever truly identical at the atomic level. Hspice tests all of this using Monte Carlo simulations. It runs hundreds of automated iterations that randomly fluctuate those device parameters. By running these massive automated Monte Carlo iterations within the foundry's strict variance boundaries, Hspice lets engineers guarantee that the chip's design will hit a 99.99% yield rate. And the craziest part? It guarantees this incredible reliability before a single atom of physical silicon is ever even manufactured. That right there is the true power of the gold standard. And finally, Section 5, powering the digital world, bridging physics and tech. Ultimately, Hspice is so much more than just a piece of software. It is the vital bridge that connects abstract quantum physics to the functional real-world tech we rely on literally every single second. So I want to leave you with this thought. Every smartphone in your pocket, every laptop you use, every highly advanced generative AI accelerator chip in existence, they all owe their survival to this quiet, plain text simulation engine. It's just running tirelessly in the background, solving millions of simultaneous matrix equations, one discrete time step at a time, to keep our entire digital world alive. Would any of this modern magic even exist without Hspice? Honestly, it's highly unlikely. Thanks for joining me on this explainer. Keep exploring, and I'll catch you in the next one.